All right, we are back. And on to section 1.4, inverse functions. So basically all inverse functions are, if you're just given points, they're the easiest thing ever because you just switch the x and the y points and you're done. Unfortunately, that's not usually how these problems end up. They give you, functions, and then you have to either show that they're inverses or prove that they're not inverses. So to show that they're inverses, what I should be able to do is I should be able to find f of g of x and g of f of x, and both of them should just produce x as an answer after they're simplified. So we're going to show that these are inverses, verify that, here's what we're doing, verify that f of g of x, again, you'll see that shorthanded, it looks like fog, kind of like FOG, like with a real little O of x. That's the same as that. That should be x, and then g of f of x should be x. And so again, you could write it like that, or you could write it like this. Those are the same thing. All right, so let's do it. So we're going to do f of g of x. So that means I'm going to take this and substitute it in where there's an x. So 2 blank to the third power minus 1. And basically we're going to sub in the g of x. So everything that's there for the g of x, the cube root of x plus 1 over 2. And now we're going to simplify this. So this and this, right, the cube root cubed, those cancel. So you have 2 times x plus 1 over 2 minus 1. And then we simplify further. This is 2 over 1, sort of. So those 2's are going to cancel. And we're going to have x plus 1 minus 1, and then combine the like terms. So f of g of x did turn out to be x, but we're not done. It also has to work in reverse, so I have to be able to put g of f of x in and show that that is. So that is going to be the cube root of plus 1 over 2. So I have to put this in there, where the x was. So 2x cubed minus 1 goes in where the x was. You can put parentheses around it, but really the first thing I'm going to do is drop the parentheses. Nothing happening there. So now on the numerator I combine the like terms. Then I reduce the 2's. And then I take the cube root of x cubed. And voila. So if f of g of x equals x and g of f of x equals x, then f and g have an inverse relationship. All right. On to the next page. That was page 15. We're on 16. So we're looking at the graphs of inverses. And so they already have the graphs on there. And here, I'll demo what I was talking about before, that if you have the x and y, the inverses will just switch the x and y, even on complicated problems like this. All right, so here, I'm going to do my best. You have the picture in front of you in the notes. So it kind of looks like that. Not exactly, but So got to use your imagination a little bit. But this is what I was trying to state before. We've got here, this guy is f of x. This guy is g of x. But when we look at like this point, that is -1, 0. But on this one, that is 0, -1. I just switch the x and the y coordinates around. And that's the inverse. So if I pick another point on there like 2, 2 on this one is 2 comma 1.14. And then on this one, it's going to be 1.14 comma 2. So I didn't do a great job of, spacing it out. It's spaced out better on your actual picture. But I'm just switching those two around. 1.14 comma 2. So I got the 2 part right. The 1.14, both of those are a little wonky. All right. And then also what you're always going to see is when they are inverses, y equals x will be a mirror. So they'll always be mirrored over y equals 1x. And so this is a weird part that you can't do with a real life mirror. This is a mirror image of that, but then it actually hits the mirror and goes through it, and it goes through it on that end. And then they're mirror images off of the rest of what exists there. So obviously we don't get to do that with real mirrors. All right. So that is that function. They already graphed it. Here, the existence of an inverse function. Function has an inverse if and only if it's 1-to-1. So that IFF isn't a mistake. Whenever you see this, that is if and only if. That is if-then statement, and then the if-then, the antecedent and the consequent can get switched around, and it's still true. And then you get to say if and only if. So if it's a biconditional, if then that, and then I flip it around, and if then that also works. That's called a biconditional, and we say if and only if. So if f is strictly monotonic, that means a one direction on its entire domain, and then it is a 1-to-1 function and therefore has an inverse function. The horizontal line test can be used to determine if a function is monotonic. Okay, so a vertical line test is to make sure it's a function. So if we looked at this and drew vertical lines there, it only is going to hit it in one spot, so it passes the vertical line test, and then does it pass the horizontal line test? So if I throw a horizontal lines just in this top one, just on the g of x, if I hit it with all the just horizontal lines, we'll only hit it once, spot, and yes. So it passes the horizontal line test, and that means it has an inverse. So if it's a 1-to-1 function, it has an inverse. It's a function if it passes the vertical line test. If it passes the horizontal line test, it's a 1-to-1 function. Also known as monotonic. Strictly monotonic. Very fancy. So that means it has an inverse. And in fact, we define the inverse. We have it graphed. And they have the actual equations, 2x to the third minus 1, and the square, or the cube root of x plus 1 over 2. So the same functions we had on the page before. All right, let's look at this one and find its inverse. Oh boy, and do a graph. So f of x is defined as the square root of x plus 3. So when we look at that, remember f of x, just a fancy way of writing y. So y is equal to the square root of x plus 3. The domain would be, we're trying to keep it in the real number system. So the domain is -3 to infinity, inclusive. It can be 0. You can take the square root of 0. And then the range of that is going to be 0 to infinity. So let's take a look at the graph, and that'll be a little more obvious of what's going on there. So when we have the square root of x plus 3, -3, sort of where it comes into existence, right there. So it can be -3. I can put in -3. -3 plus 3 is 0. Square root of 0 is 0. So -3, 0 is a point. Then I could put in -1 and -2 or 0. That would be the square root of 3. Or here, 1, 2, 3, 4, 5, 6. Let's put in 1. 1 is the square root of 4, which is 2. Right? And then 1, 2, 3, 4, 5, 6. That's 6 plus 3 is 9. The square root of 9 is 3. So we got 6 comma 3. We got 1 comma 2. And we got -3 comma 0. So those are our points. It's sort of like half of a parabola. Oh, jeez. I tried to erase it with my fingers and it made it worse. 1, 2. Okay, let's try this again. There you go. There it is. All right. So, is it a function? Yes. Passes the vertical line test. Is it a one-to-one function? Well, yeah, it's going to pass horizontal line test also. That is, if I draw any vertical line, it'll only hit it in one spot. If I draw any horizontal line, it'll only hit it in one spot. So that means it's a one-to-one function, which means we can define the inverse. We've got the domain, -3 to infinity inclusive, and we've got the range just on the upper half, so 0 to infinity, so just above the x-axis. All right? So now, to find the inverse, what you do is you kind of swap out x and y and then solve for y. So what I'm going to do is I have y equals the square root of x plus 3. What I'm going to do is I'm going to actually swap them. So I'm going to have x equals the square root of y plus 3. And now I'm going to solve for my new y. So how do I solve that? I square both sides to get it out of the square root sign. And then I isolate the variable, subtract the 3. So I got y equals x squared minus 3. Now, if my original function was f of x, I will call this f inverse of x. So I'll put a little -1 on there. That way it won't be confusing with the y's. All right, so there is my inverse function. What is that going to look like? Well, the domain and the range are going to be swapped out. So when I look at this, that's a parabola that opens up, but because I did it as the inverse of this function, it's y equals x squared, but it can't exist over here because I've got to use the range as in the domain. So my range is going to be from -3 to infinity, and my domain is going to be from 0 to infinity. So that means it doesn't come into existence until 0. So I put 0 in, and then 1, 2, 3. I get -3. And then again, I can put in 2. 2 squared is 4. 4 minus 3 is 1. So 2 comma 1 is just that flip-flopped around. And then 3 comma 6. If I put a 3 there, that's 9. 9 minus 3 is 6. So 3 comma 1, 2, 3, 4, 5, 6. That's up there. And now I do that graph, but it's only that half of the parabola. It isn't the other half. Even though this is defined as a parabola, that would open up and I'd have x squared, but this part can't exist because I built it off an inverse of that, so I have to stick with the inverse domain and range. All right. Now let's take a look at what we got next. Show that the sine function is not 1-to-1. Okay, that's easy enough. That'll be a quickie. So the sine curve is a function because it'll only hit, if I do, it passes the vertical line test. So it is a function. But now, is it a 1-to-1 function or what do they call it? Monotonic. Meaning, so it passes the vertical line test. Anytime I draw a vertical line, it only hits it in one spot. But will it pass the horizontal line test? And the answer is no. Nope, it fails. If I draw a horizontal line, it's going to hit it in more than one spot again and again. And it only has to fail in one spot, but it fails again and again and again and again. Right? So the only one spot that it would not fail is at the max and min, and it doesn't matter. It just takes one failure and the whole thing is out. So it is does it pass the horizontal line test? No, it's not 1-to-1, which means it doesn't have an inverse. So we only use a monotonic portion of the graph and the inverse of that portion. So what they basically do with the sine curve then is they cut it from -90 to 90. And that's where they define the inverses. That's why your calculator, when you take the arc sine of things, it uses this domain from -90 to 90. So you cut it there. So when we do the arc sine, like y equals the arc sine, that basically, it looks a lot like this. It's just flipped a little bit. So you can look at the drawing on your notes. I'm not going to try to do that. But the domain is -1 to 1, and the range is -90 to 90. And they've got a picture of it. So this is a picture of just this cut out, you know, from here to here. That's what I did there. But to do the inverse, the y equals arc sine, then this goes -1 to 1, that goes 90 to -90, and that's the picture that you get. All right, inverse trig ranges are restricted to one positive quadrant and one adjacent negative quadrant. Okay. So basically, find the inverse analytically, algebraically of the sine. Okay, let's do that. So when we think about where this exists, -90, think about back to the unit circle. What's going on there? So arc sine is only going to exist from 0 to 90 and -90, which is 270. And so that the arc sine is there and there. Same as the arctangent. The arc cosine, that one they take from 0 to 180. So the arc cosine ends up in 1 and 2, not 1 and 4. All right, so to find algebraically here, y equals the sine of x, and from -90 to 90, or I should get used to using pi over 2, pi over 2. Radians, pi over 2 to pi over 2 radians. So we're going to, basically what we're going to do, we're going to take the arc sine of both sides. And so we end up with the arc sine of y. That is a different way of writing it. This is the exact same thing. You can write sine -1y or arc sine y. And then the arc sine of the sine of x would just be x. Because you're asking what angle gives you the sine of this, and so it's just going to be back to x. Then you switch up the x's and the y's. Remember how to find it. And so we have arc sine of x is equal to y. And so the inverse function of x is the arc sine of x. And now the range is -90 to negative pi over 2 to pi over 2. Is the range. Okay. So on page 18, an arc trig function gives an angle. So let's see, the function y equals arc sine x if and only if sine of y equals x. If and only if. So that is biconditional. You could switch if-then statements, the antecedent and the consequent. And you would get the same thing. It would both be true. So like an if and only if would be, if I multiply by 0, then I get 0. If I get 0 through multiplication, then one of the factors has to be 0. So you can switch up the antecedent and the consequent, and instead I could just say if and only if. All right, so let's see. They want me to take the arc sine of negative 1/2. And so, let's take a look. We've got the sine, remember coleslaw. And we're looking at 1/2, so that's pi over 6. So that's 11 pi over 6. And the cosine, I mean, we could put the cosine in there from our little trick. Let's go to 3 over 2. Comma negative 1/2 is what's going on there. And so because we only are looking for the sine, the arc sine negative 1/2, we are only looking for the arc sine in the first and the fourth quadrant. From negative, remember this is negative pi over 2, and this is pi over 2. So we're only living in that part of the, for sine. So that's why we knew it wasn't over here and wasn't over there. So anytime it's the arc sine of a negative number, you're going to be in quadrant 4, and when it's the arc sine of a positive number, you're going to be in quadrant 1. All right. And now they want the arc cosine of 0. The arc cosine of 0. Okay, so again, our cosine, we're only living in the first and the second quadrant. And so when we look at that, right, coleslaw, we got 1, 0, 0, 1, negative 1, 0, but slaw. So when is the cosine 0? Then that's going to be 90 degrees, or pi over 2. Oh, and I should have said on this one equals 11 pi over 6. So again, what does that, remember what this means. This means here, the long way is y equals arc sine negative 1/2. And so I could take the sine of both sides. But really, that and that are going to cross each other off. So I'm just going to have the sine of y is equal to negative 1/2. So when is the sine of y equal to negative 1/2? And 11 pi over 6. So arc cosine, oh, I left a c off of there. Arc cosine of 0, that's going to be pi over 2. That again is asking the cosine of what angle is 0. But it's got to be from just 0 to 180. All right, and they have the graphs on there, the arcs. So you want to look at your notes. So page 19, they got the arc tangent of square root of 3. So what is that going to look like? So remember the arctangent. This is the top of page 19. That is going to be tangent lives in the first or the fourth quadrant. Those are the only two we're going to look at for these. So we have y is equal to the arctangent of the square root of 3. So if I take the tangent of y, that's equal to the tangent of the arctangent of the square root of 3, which is just the square root of 3. So they want to know when is the tangent equal to the square root of 3. And so you got to think about that. It's going to be remember, tangent is the sine over the cosine. And so how are we going to end up with a square root of 3 there? In either the first or the fourth quadrant. But both of those are going to have to be positive to be that. So we're only working in the first quadrant. So let's do our little trick. Pi over 6, pi over 4, pi over 3. Sine, cosine, 1, 2, 3, 3, 2, 1, over 2 on all of them. That square roots on the top. And then remember the square root of 1 is just 1. That's why I keep skipping those. So you can just kind of square root those in there. So which one is going to give us the square root of 3 on the sine over the cosine? That's going to be pi over 3, right? This over this. Because, right, that is the square root of 3 over 2 divided by 1/2, which is the same as times 2 over 1. And there's our square root of 3. So that's got to be pi over 3. Y has to be pi over 3. All right. And then the last one, use a calculator. So I don't need all of this for that. Do the arc sine. So you hit second sine. That is the arc sine of 0.3. And that kicks out 0.3047. Oh, make sure you're in radians. If you just type that into your calculator and it didn't kick out 0.3047, make sure you are in radians. All right, and now let's take a look at the next one. The tangent of the arctangent. So that's way easier than this one was. Tangent of the arctangent of -1 over the square root of 3, which is -1 over the square root of 3. And then you fix it because we can't have a square root at the bottom. So multiply top and bottom by the square root of 3. So we'll call it negative square root of 3 over 3. Be aware of domain restrictions here when we have the arc cosine of the cosine of 5 pi over 4. Okay. So again, we're restricted in the domain. The arc cosine of the cosine of 5 pi over 4. But remember, our cosine is restricted to just the first and the second quadrant from 0 to 180, the principal values. And so 5 pi over 4 lands you in the third quadrant, but we can fix that so that it falls into either the first or the second quadrant. So that is 5 pi over 4, which is, I keep erasing it. I gotta just leave that, the little cheat sheet guy up there. The square root of 2 over 2, right? And so, all-star trig class. All-star trig class. And so, 5 pi over 4. Cosine would only be positive here and here. And so, since we're restricted into the first or second quadrants, when I take this, I'm looking at negative square root of 2 over 2, comma, negative square root of 2 over 2. And remember Coase law. So the cosine of 5 pi over 4 is negative square root of 2 over 2. But now, if I take the arc cosine of that, it's going to kick it back into the second quadrant. Because it's got to be in the first or the second quadrant for the arc cosine. And so I do the arc cosine of that and end up with the 3 pi over 4. Because, right, it's 4 pi over 4 minus pi over 4 is 3 pi over 4. Okie dokie. Then C. Yeah, they got a little mix and match there. For C, they've got the arc sine of the cosine of 2 pi over 3. All right. And so we've got, oh no, we don't have 2 pi over 3 up there. Okay, let's draw 2 pi over 3. That is pi over 3 in the second quadrant. And so we're looking at negative 1/2, comma, square root of 3 over 2. That's Coase law. So the cosine of that is negative 1/2. But then they want the arc sine of negative 1/2. And so that's going to be back into, remember where sine lives, the arc sine lives in the first or the fourth. Since it's a negative 1/2, that's bumping me here. And so I'm going to use the 11 pi over 6. Because they switched sign. So we're not on pi over 3s anymore. Pi over 3 was just to get us that. Now we're on pi over 6. To get me my my square root of 3 over 2 and negative 1/2. And so to get there, that's 12 pi over 6 minus pi over 6. So that's going to be 11 pi over 6. So that was tricky because you had to use the cosine to find it, the negative 1/2, but then you had to switch to sines. And so That's 60 degrees for sine and 30 degrees for cosine. Or the other way around, 30 degrees for sine, 60 for cosine. All right. Solve the equation, the arctangent. Oh boy. Hopefully this is all coming back to you from your pre-calc days. A lot of trig. You really have to have this stuff down in order to be successful in our Calc 1 course. This chapter 2, 3, 4, 5, and 6, just take all of this for granted that you know you are very familiar with all of the things I am reviewing right now. All right, so let's take a look. We got 2x minus 5. Oh, the arctangent of 2x minus 5 equals pi over 4. So let's do the tangent of both sides. And that'll free up this. So the tangent of the arctangent of, it just gets me 2x minus 5. And then the tangent of pi over 4, that's 45, 45, 90. Remember, that's square root of 2 over 2 over the square root of 2 over 2. I mean, you could draw it. But remember, it's sine over cosine, so that's just 1. Tangent 45 is 1. And now we just go back and solve. Thank goodness. An easy one, finally. Good to have an easy one once in a while. So x equals 3. All right. And then that is it for this video. We'll do 1.5 next.